To understand radioactivity, we need to understand atoms. So we should all be fairly familiar with a diagram like this, which shows us a model of the atom. We've got protons with a positive 1 charge and a mass of 1, neutrons with a neutral charge of 0 and a mass of 1, and electrons have a negative charge and a relative mass compared to the other two of 1 over 2000. Now it's important to note this diagram is very much not to scale. The electron should be a lot smaller, but also the size of the atom we need to know is about 10 to the power minus 10 meters. A nucleus is even smaller, about 10,000 times smaller, which will give it a rough diameter of 10 to the power minus 14 meters. So how did we get to this point? Let's have a look next at the development of the atomic model and how it developed over time with new evidence. So one of the earliest ideas of the atom was that it was a solid sphere. So that means that it's indivisible, it can't be divided up further. This idea persisted up until around the late 1800s when electrons were discovered. So with electrons being discovered, that means they've got a negative charge, there must be a positive charge in the atom as well. So one of the early models that explained this was the plum pudding model put forward by J.J. Thomson. He said that the atom was like a plum pudding, which is sort of like a chocolate chip muffin. You've got this ball of positive charge, which would be the muffin, and then you've got these electrons distributed evenly, which would be like the chocolate chips. Now, the next thing that came along to cast doubt on that was the alpha scattering experiment, which was done by Ernest Rutherford. Now, this led to the development of the nuclear model, which had a positive nucleus, which was small and dense, and had electrons that were negative orbiting around the edge of the atom. And in between, there was mostly empty space. Most of the atom was empty space. Now, this seemed like quite a radical idea at the time, and it could only be put forward due to very strong evidence from the alpha scattering experiment. So the alpha scattering experiment fired alpha particles via an alpha source at a thin gold leaf, and it had a big detector on the other side to see where the alpha particles went. Now, this had to take place in a vacuum, so there was no collisions with air molecules that would disturb the experiment. The evidence it discovered was that almost all the alpha particles went straight through the gold leaf, which was kind of as expected. That would have happened if the plum pudding model was correct. However, some of the alpha particles were deflected by the atoms in the gold, and very few, 1 in about 10,000, were deflected by really large angles. So when we say angle, we mean the angle that the beam would make compared to if it went straight on. So these large angles basically meant it would bounce back and come the other way. So let's look at next. So what did that evidence lead Ernest Rutherford to conclude about the atom? So the fact that most alpha particles went straight through, he concluded that most of the atom must be empty space. The fact that some of them get deflected by atoms in the gold led him to conclude that there must be a positive region, a quite dense positive region, which had enough charge to deflect alpha particles. Now, alpha particles deflect because they have the same charge as the nucleus. So for them to come close together, that would mean they're going to repel because they have the same charge, and like charges repel. The closer they go to the nucleus, the greater the force they're going to experience. Now, the other conclusion was that the nucleus must be very, very, very small with all the atoms positive charge there, and they would explain the idea that very, very few of these particles would deflect straight back or at a very large angle. Because they're getting so close to the nucleus, they experience a stronger force, which is going to have a larger deflection, as seen in the diagram here. So when the alpha particles come close to the nucleus, this is what happened. This was unexpected. With the plum pudding model being correct, they would expect all the alpha particles to go straight through. Now, this was because even though there were positive and negative charges inside the atom, that they're so evenly distributed and the negative charges are so small that actually it would have very little effect on those alpha particles. A really important part of the development of the model of the atom is the idea of evidence. So this is a really good example of new evidence coming to light via an experiment that does not support the plum pudding model theory, and it does support or lead rise to a new theory, which was the nuclear model. Please don't say things like it gets disproved or things like that. It's only evidence that can be provided to support a model. Now, we might notice in a nuclear model, the electrons are orbiting sort of all over the place around the nucleus. The next development was Niels Bohr, and this leads to the Bohr atom. In the Bohr atom, it is very, very similar to the nuclear model, but the electrons are orbiting at fixed orbits or in shells around the atom, where they cannot just orbit anywhere. Another thing the Bohr model was able to explain was the idea that electrons can change between electron shells. So if an atom absorbs electromagnetic radiation, then what that allows it to do is that the electron can move to a higher energy level or a higher energy shell. So it gets promoted to the next level up. Conversely, if the electron goes back down to a low energy level, that results in electromagnetic radiation being emitted or given off. This is an example of energy conservation, where EM radiation being given off means the electron has lost energy, so the energy gets emitted as EM radiation. The last little step on our journey is the neutrons, which were discovered quite late, quite a couple of decades after the nuclear model. This is because they have no charge, they're very difficult to detect. And this was done by James Chadwick, who discovered the neutron and led to the atom looking like it does on the right-hand side of the screen as our model. Next up, we're focusing specifically on the nucleus, in particular, how to work out how many protons and neutrons are inside a nucleus. So in this example here, I've got some carbon-12. As you can see from the diagram, we count them up. There are 6 protons and there are 6 neutrons. So the atomic number is the number of protons. So in this case, that will be 6. The mass number, the bigger number usually at the top of the element symbol, is the number of protons plus the number of neutrons. So in this case, that happens to be 12. To work out the number of neutrons, you do the mass number minus the atomic number. Now you can have the same element, in this case carbon, with a different number of neutrons. So if I add 2 extra neutrons in here, so that it's now got 8, the mass number will change to 14. The isotope is defined as an atom that has the same number of protons, but a different number of neutrons. So in this example, 2 isotopes of carbon would be carbon-12 and carbon-14. Note that the element is the same because there's the same atomic number. And because of this, they must both have the same charge in the nucleus because they've got the same number of protons. For an atom to have a different charge, it's called an ion. An ion is defined as an atom that has gained or lost 1 or more electrons, just like you would have learned in chemistry. Normally, for an atom that is not an ion, you're going to have the same number of protons as there are number of electrons to make the atom balanced in terms of charge. But with an ion, the electrons has changed, so therefore it is now got an overall positive if it's lost electrons or a negative if it's gained electrons. I've used the example of carbon-14 here because it is radioactive. So what is it that makes it radioactive? Well, any radioactive nucleus is said to be unstable. It can happen with different types of nucleus, but they all have that thing in common, they're unstable, and it's usually due to an excess of protons or neutrons. So when an atom is unstable, there is radiation emitted. Now this radiation emitted when an unstable nucleus decays can either be alpha, beta, or gamma radiation, or sometimes just pure neutrons. So how do we work out which type of radiation it is? Well, we need to have a radioactive source and we need to have something to detect the radiation. That's called a Geiger-Müller tube or a Geiger counter set up close to the radioactive source. The Geiger-Müller tube is hooked up to a counter which is going to measure the count rate. The count rate is defined as the number of decays measured per second. At the radioactive source, the number of decays per second is called the activity. That's the number of decays in the actual source per second, and that's measured in becquerels or BQ. Now it's important to note the difference between activity and count rate. They both look like the same definition, but the count rate is the number of decays per second that are measured, whereas the activity is the actual number of decays per second. That's because some of the radioactive particles or waves will go outside of the detector and won't be picked up. So how do we figure out which type of radiation is in our source? We use something called an absorbing material, and depending on the absorbing material, we could be able to figure out whether it's alpha, beta, or gamma radiation. So let's do a little summary table then of all the different properties of alpha, beta, and gamma radiation. We can also look at what they are, which can help us figure out what their properties are. So we're going to look at their range in air, if there's nothing stopping them. We would look at what material stops them or is absorbing the radiation. Are they ionizing or not? And also, what is it? So alpha radiation first. Now in the air, if you put the Geiger-Müller tube anything greater than 5 centimeters away, it wouldn't detect it. So the range is 5 centimeters. It's stopped by anything as thin as paper. Could be human skin as well, but paper is the thinnest thing. And it's very ionizing. An alpha particle is made up of 2 protons and 2 neutrons. Beta particles, on the other hand, have a range of up to a metre in air. They're only stopped by a thin sheet of aluminium, and they are ionising, but only moderately ionising, not as much as alpha radiation. A beta particle is an electron. Gamma radiation can travel many kilometres. Realistically, you could say it's infinite range. It's only stopped by very thick lead or very thick concrete, and it is ionising, but only very weakly ionising. Gamma radiation, we might remember from the waves topic, is a high-frequency electromagnetic wave, or EM wave. And neutron, we don't need to worry about the properties of here for GCSE. Now, if we consider all the different air molecules, we can help explain these properties using the idea of ionisation. So let's start off with gamma radiation. Gamma is not very ionising. What that means is when it encounters a molecule in the air, it is unlikely to ionise it. So it's unlikely to go through all the air molecules to the other side, so it has a high range. Beta, on the other hand, is moderately ionising, so might ionise some of these atoms, and it will lose energy each time and eventually stop after around about a metre on average. Alpha radiation, on the other hand, is very ionising, so it's likely to ionise lots of atoms very close to it, meaning that it's going to lose lots of energy very quickly, so it can only travel a few centimetres in air. Let's look at the uses of each of these types of radiation and see if we can link their use to what are their properties. So alpha radiation is used in smoke alarms. This is because it's highly ionising. It ionises air to allow a current to flow between 2 points. When smoke particles get into the smoke alarm, that stops the current flowing because smoke particles are not charged, just like in the diagram shown here. Beta radiation is used to monitor the thickness of aluminium foil. Beta is suitable because if too much will go through, that would show the foil is too thin. If not enough go through, that may mean that it's a bit too thick. So it's only beta that can be used because some of it gets absorbed by a thin aluminium foil, but some of it will go through. Gamma radiation is used in radiotherapy. This is used to destroy cancerous cells in the body. Now, it can destroy them because it's weakly ionising, but more importantly is that the radiation can get through the skin and into the body, unlike alpha and beta can't do that. Let's look next at nuclear equations. So we have a mass number and an atomic number for alpha radiation. An alpha particle has 2 protons and 2 neutrons, which means it's got an atomic number of 2 and a mass number of 4. You might notice this is exactly the same as helium, but it will be a nucleus of helium in this case, and you need to be familiar with using that instead of the alpha symbol. So let's look at an example. I've got uranium with an atomic number of 92 and a mass number of 235, and it's going to decay into thorium plus our helium nucleus alpha particle. You know that the helium nucleus is an alpha particle, so that's going to have 2 and 4 as the atomic and mass number. And if we compare the left-hand side to the right-hand side, if the uranium nucleus has lost 2 protons, that means that the atomic number is going to go down by 2, which in this case means it goes from 92 to 90. The mass number has lost 4, so that goes down to 231. So we can fill in those atomic number and mass number for our new element, thorium. Beta is a little bit trickier. So a beta particle has a mass number of 0 because there's no protons or neutrons in it, but it has an atomic number of -1. I'll explain why that happens in a second. You can also use a beta particle. Instead of a beta particle, you can use the symbol for an electron to represent it. It's the same thing. So let's look at an example. Let's take our carbon-14 from earlier, and that's going to decay into nitrogen. And then it's going to have a beta particle be emitted as well. Now, when the beta particle is emitted, we can see the mass number does not change. So therefore, the mass number of nitrogen can't change. So therefore, it's now 14. The atomic number, on the other hand, the atomic number of our beta particle is -1. So something plus -1 has to equal 6. In this case, that's going to be 7. So the atomic number is actually increased from 6 to 7. Now, the reason this happens, and this is really tricky to get your head around, is that inside the nucleus, a neutron has changed into a proton. It sounds like magic, but that has actually happened. Now, when that's happened, that means the atomic number has gone up by 1, but the mass number hasn't changed because the atomic number would go up by 1 for an extra proton, but down by 1 because it's lost a neutron. So the number of protons and neutrons hasn't changed, hence why it stayed at 14 in this case. Gamma radiation, you wouldn't find any nuclear equations with because it does not affect the mass number or the atomic number of our unstable nucleus. Radioactive decay is random. You cannot tell when an individual nucleus will decay, but we can use the idea of half-life to make predictions based on large numbers of nuclei. The definition for a half-life is the time taken for the number of nuclei to decrease by half. The number of nuclei could instead be the activity or the count rate. So if we look at a graph here, if I've got number of nuclei against time, if I wanted to find the half-life, I would take the number of nuclei at the start, in this case it's 1,000, I'd go down to half that, in this case 500, and I'd go along, read off the graph to see what the half-life is. That will be the time taken for that to happen. Now we should notice every time the number of nuclei halves, so 500 to 250, 250 to 125, it should take the same amount of time to halve, so the half-life is constant. So in this way we can actually make it all predictable. It's a random process, but we can predict for large numbers of atoms how many might decay in a certain time frame. So let's look at a couple of examples, because these are the kind of questions that can often catch people out. So what is the half-life of a substance that initially has 3,200 nuclei, and after 9 days it now has 400 nuclei? So the first step is to figure out how many times it's halved. So 3,200 halved once is 1,600, halved again is 800, and halved again is 400. That means it's halved 3 times. So 3 half-lives have taken place in 9 days. That means that in 9 days, 3 half-lives means that 1 half-life is going to have a half-life of 3 days. In example 2, it says what percentage of atoms have decayed after 400 years if a substance's half-life is 100 years. So we've got to figure out, after 400 years, if the half-life is 100 years, how many half-lives is that? So 400 divided by 100 gives you a half-life number of 4. So in 4 half-lives, we've got to figure out what percentage we get left after 4 half-lives. So 100 to 50 is 1 half-life, 50 to 25 is another, 25 to 12.5 is another, and 4 half-lives means it's halved 4 times down to 6.25%. Now this question is a bit sneaky. It doesn't ask what percentage are left, it asks what percentage of atoms have decayed. So therefore, if we do 100% minus 6.25, that means that 93.75% of atoms have decayed. For medical uses, a half-life of a few hours is quite common. The reason if it's too much longer than that, the radioactive source will be in the person for way longer than they're in the hospital, and too short means that they can't do any measurements involving it. Let's have a look at 3 different examples here. I've got 3 sources, uranium, potassium and carbon, and I've got their half-life. Now I have made most of these half-lives up just to make a point, but it could be any different elements given to you in your exam. So the question would ask, which source has the biggest hazard if you ingest it or if you eat it? Now to understand this, we've got to understand the idea of activity. On the previous part of the video, we looked at activity being number of decays per second. Now for this graph of number of nuclei versus time, the activity, number of decays per second, or the rate of decay, is going to be highest at the start where the gradient is really steep, and it's going to be lowest near the end where the gradient is more shallow. So actually the shortest half-life is going to be the biggest hazard because it has the highest activity, the highest number of decays per second. That's going to provide the biggest dose to a person if it gets absorbed into their body. Now, talking about hazards from radiation, let's talk about 2 really important key terms, which are contamination and irradiation. When something is contaminated, what it means is that there's an unwanted presence of radioactive material that's inside the object, material, or the person. On the other hand, irradiation refers to something being exposing an object or a person to nuclear radiation. Note that that does not make the item become radioactive, it's just being exposed to it. So an example of contamination would be swallowing a small amount of a source by accident, or potentially water from a power station leaks into the surrounding soil. The thing is now contaminated because it's got the radioactive material inside it. Irradiation, an example, would be pointing a radioactive source at someone. Not a good idea, but it does not make the person radioactive, it just exposes them to radiation. So generally speaking, irradiation would be less dangerous. Now to avoid these 2 things, if your teacher has shown you reactive sources in a classroom, they would take a number of precautions. They usually wear gloves to avoid the material getting on their skin and then getting inside them later. They usually use tongs to keep a big distance between them and the source, and they'll probably wash their hands after use for the same reason as they wear gloves. Now, other people in the room need to make sure they stand at least 2 meters away to reduce the chance of becoming irradiated, and the sources themselves need to be kept in a lead-lined box. So to prevent the source radiation leaking out from the box. You're only supposed to have the sources out for as long as you need them for. You don't want to leave them on the side of a classroom or a room any longer than you want to use them. Therefore, you are minimizing the exposure time to the class or to whoever you're showing them to. Now, despite these dangers, radiation is around us all the time in the form of background radiation. Background radiation, as the name suggests, is radiation that's around us all the time. We can't really do anything about it. It comes mostly in the UK from radon gas, about 50% from radon gas, which is from rocks, in particular areas like Devon and Cornwall that have a lot of granite. The other background radiation sources, some of them are artificial, so this would be from nuclear weapons fallout, usually from decades ago. This might be from nuclear power stations and also from medical sources. You also have a certain amount of background radiation from food and drink, from radioactive foods like bananas, quite famously, and also cosmic rays, which are rays from outer space, especially if you have a job where you're flying on planes a lot. Now, radiation dose is measured in something called millisieverts. Sieverts you don't need to know as the unit, but it's a good example of just being familiar with it so you don't get put off in questions. Now, millisieverts means 1,000 millisieverts is 1 sievert, or 1 millisievert is 1,000th. So it's a good opportunity for exam questions to test how can you compare different dangers with things like this. So, for example, if we look at the different millisieverts of dose for each of these, we'll find that cosmic rays, for example, might have 1.6 millisieverts per year. We might find a banana on average has about 0.00098 millisieverts. That should say millisieverts, not sieverts there. And we've also got each of these will have different amounts of dose associated with them. Compare them to the dose for fatality, to die. That would be 10,000 millisieverts or 10 sieverts. So even though it's not great to have background radiation all the time, it is never going to be anywhere near enough to kill you, even if you have quite a few x-rays. So we'd be careful with it, but it's not much in comparison to what would be needed to actually kill someone. Okay, the last part of this section of the video is all about fission and fusion, which is only if you're doing triple science or separate science. You do not need to worry about this if you're doing combined science. So let's look at nuclear fission first of all. Make sure you're spelling this correctly. So nuclear fission, there are two types. There are spontaneous and induced fission. Nuclear fission is defined as the splitting of a large nucleus into two smaller nuclei, which releases neutrons and energy in the form of gamma rays. Now, spontaneous fission is very rare and it would occur naturally in fuel like uranium in the ground. Much more likely is induced fission, which means it has happened artificially. Now, this occurs when uranium or a plutonium nucleus gets hit with a slow-moving neutron. The slowly moving neutron is absorbed into the uranium. It does not pass straight through, but it gets absorbed. The uranium will then split into two. Now, the fragments it splits into, you don't need to be familiar with, but it will be two similarly sized elements, about half the size of a uranium nucleus. And when that happens, it will release between 2 and 4 neutrons. When those neutrons then carry on going, something called a chain reaction can happen. If they encounter 3 more uranium nuclei, the same process can happen again if they're absorbed by the uranium nuclei and then the uranium nuclei split again, releasing neutrons. So you might have, just from 2 different reactions, you have got 9 neutrons, and you times by 2 or 3 each time, there are lots and lots and lots of energy released, which is what might result in a nuclear bomb or a nuclear explosion. Now, we can harness this in a nuclear power station to use it usefully. We do not want a nuclear bomb. So to be able to do this, we need to have a few different things in our nuclear power station. So control rods are a big part of a nuclear power station because they allow us to control the rate of reaction. They absorb the neutrons, so take in the neutrons, so they reduce the rate of fission. They reduce the chances of those neutrons going on to cause more fission. A moderator is another example of something in a nuclear power station. This slows the neutrons down so they can actually be absorbed by uranium in the first place. You'd also have thick concrete shielding, and we'd need to know in a nuclear power station, the rest of the power station is identical to what you'd find in a coal power station, for example. You have heat that drives steam, heat water drives steam, which makes a turbine turn, and then you have a generator to convert it to electricity. Nuclear fusion, on the other hand, is the opposite process. Fusion is the joining together of 2 light nuclei to form a heavier nucleus. And as that happens, a small amount of mass is converted into energy. This is given by the equation E equals mc squared, which isn't on the GCSE spec, but sort of helps explain how those two things are linked. Now, nuclear fusion is very difficult to make happen because you've got two hydrogen nuclei, the lightest elements. They both have a positive charge. So to make it fuse together and turn into a new element of helium, you're going to need really high temperatures and pressures. This is so the particles have enough kinetic energy or enough speed to overcome electrostatic repulsion so they can come together in the first place. And that's the end of the topic on atoms and radioactivity. I hope you found that really helpful. Make sure you revise this topic as it's one of the trickier ones that comes up on a lot of papers.